These are notes on nuclear fission and fusion. It's section 25.3 in your book, and it's going to cover bombs, clean power, and the sun. So we're going to start with nuclear fission. Nuclear fission is the splitting of the nucleus of an atom. So fission means to split something into two pieces. So nuclear fission is splitting the nucleus. So it uses certain heavy isotopes. There's a uranium isotope and a plutonium isotope that are both fissionable. And basically these isotopes are bombarded by neutrons. Once their nucleus has more neutrons, it becomes incredibly unstable. You remember that nuclear instability has to do with a ratio of neutrons to protons. And so it becomes so unstable that the entire nucleus actually splits apart into two different separate nuclei. And then you get a chain reaction when the neutrons produced in one fission reaction hit other fissionable isotopes. So I'm going to show you a diagram of that in a second. And this kind of nuclear reaction, nuclear fission, is what was used in the atomic bombs that were used in Hiroshima and Nagasaki in the Second World War. And this is also what's used in nuclear power plants. However, one thing to note is that the type of the purity of the the purity of the uranium that's needed for an atomic bomb is very different than the purity needed for a nuclear power plant. So I know some people say, well, we shouldn't pursue nuclear power because somebody could take that and turn it into a bomb, and that's not in fact the case. That they're two different percent purities for the uranium. And so here's kind of what the before picture would look like. So here, let's get a pen. So here is the plutonium nucleus right here, and it's hit by a neutron. And your book actually has a really good kind of intermediate stage in this, where it then shows, this picture doesn't have it, a highly unstable nucleus, because of course once that plutonium nucleus has an extra neutron, it's now less stable than it was before. I don't know offhand what plutonium's half-life is. Uranium, we know, is about 4.5 billion years old, but or billion years. But once that neutron hits, it makes the plutonium nucleus much more unstable. And so what happens is it actually splits into two nuclei, and then it has some extra neutrons as well. And those extra neutrons can then go and hit more plutonium nuclei, and then those can hit more and more and more. And that's what this chain reaction up here is. So that's what really made both nuclear power and nuclear bombs possible, was this discovery of how to sustain a chain reaction, that you could have many plutonium or many uranium nuclei, and once you get that reaction started, it's going to sustain itself. It's going to continue by itself because in that reaction extra neutrons are produced. And then you also have all of this energy that happens. And that energy, if you're interested in looking at it, comes from something called a mass defect. And the mass defect is that there's, even though all the particles seem to be here, there's actually more mass in the before part than there is in these smaller fragments. Even though if you counted it all up, the mass would all be there. And that's this weird sort of like, okay, so where did the mass go? How can there be, when you actually measure it out, there be less mass? Well, that mass got transferred into energy using Einstein's equation of E equals mc squared. And that was kind of the big discovery that led to nuclear reactions being so powerful, is that a little bit of mass speeded up by the speed of light squared produces a ton of energy. And so if you're interested, again, I would look up that idea of mass defect. One of the things that makes nuclear fission so dangerous, whether you're talking about nuclear power plants or nuclear bombs, is that you're talking about radioactive atoms. And so, in addition to a lot of energy being released, there's also, you end up with radioactive waste. And that radioactive waste, which is then usually buried or somehow tried, to sequester it away somewhere for nuclear power plants, because that's a very controlled thing. That's what made something like the nuclear bombs that were dropped on Hiroshima and Nagasaki so dangerous. Not only was it this extra super big powerful bomb, but then there was all this contaminated matter all over the place, and so radioactively contaminated. And so people then, years and years later, we became allies with Japan. We're allies with Japan today. We became allies with Japan pretty soon after the war, and yet 30 years later, people were still ending up with cancer from a bomb dropped in the 40s. And so that's a big problem with nuclear bombs. I suppose for people who make weapons, that's a great thing about a nuclear bomb, is that it's so dangerous and so harmful, and you can still be feeling the effects 30 and 40 years into the future after you've dropped that bomb. So I guess it sort of depends on your perspective. If you've read, the Hunger Games, that Katniss is sort of, by the third book, she's really horrified by some of the weapons that District 13 is coming up with because she sees how harmful they could be. Well, it depends on what side of that war you're on, whether you want really harmful things or you don't. So then on the flip side, there's nuclear fusion. To fuse something together is combining. So sometimes you might hear that somebody's bone was fused together after a break. So that means to combine. It's the combining of nuclei when we're talking about nuclear fusion. And unlike nuclear fission, which uses really large elements, nuclear fusion uses really small elements. And in nuclear fusion, it essentially takes more energy for there to be two separate nuclei than for the combined one. And so that's why, again, you have so much energy that's released. And you do get this massive release of energy. And part of the problem with nuclear fusion is that the energy released is so large that it produces these incredibly hot temperatures, and it's hard to control. And so, for example, we find nuclear fusion in the sun. That's what sustains the sun's energy. The sun's energy is not a combustion reaction. It's not like a candle burning and consuming oxygen. It's the product of nuclear fusion. It's hydrogen atoms fusing together into helium atoms and then subsequently fusing into heavier and heavier and heavier atoms. And it's not until that process of fusion can't take place anymore that a star will actually die. You also see it in hydrogen bombs. So if you like that whole bomb side of things, both fission and fusion bombs are nuclear bombs because they have to do with an element's nucleus. But then atomic bombs are the fission bombs like the ones dropped in Japan. Fusion bombs have much more energy, much more power behind them. They have never been used against people. Those are what are called hydrogen bombs. One thing that's interesting about a fusion bomb versus a fission bomb is because you're using hydrogen instead of these large radioactive elements, you don't have that radioactive waste issue. And so if we could find a way to properly control fusion in a way to make energy, that would be great because you'd have this great source of energy without having the radioactive waste that's such a problem. Going back to the bomb issue, you then have a bomb that releases a ton of energy without the radioactivity. Well, those of you who are humanists might think, well, that's a great thing. Then you have this great bomb, but you don't have the radioactivity. Well, this was seen as not a good thing to people who made hydrogen bombs because that radioactivity is such a powerful weapon, such a powerful deterrent, that most hydrogen bombs are actually encased in atomic bombs. And so you get the huge release of energy, plus you get the radioactivity that goes along with an atomic bomb. So in fact, the energy from the hydrogen bomb actually starts the chain reaction for the atomic bomb, and you get both in one. Again, it sort of depends on what side you're on whether that's a good thing or a completely horrific thing. And then this is kind of what fusion looks like. So here you've got what's called deuterium. So these are isotopes of hydrogen. So here's hydrogen. They both have one proton. You can see the proton there and the proton here. But then hydrogen, the most common isotope of hydrogen, has no neutrons. Deuterium here has one neutron, and tritium here has two neutrons. So you have a mass number of 3 and a mass number of 2. And when those are fused together, it forms this vaguely unstable product, which then becomes one neutron and a helium nucleus. This actually should say 4. That's a mistake on my part, so we'll change that to 4 there. And then, again, a massive amount of energy reach. We're talking like 40 million degrees in fusion reactions, which is, of course, why the sun is such a driving force for energy in our planet. That we do use that energy, we just use it as we capture it from the sun. So please feel free to put any questions on YouTube or ask them in class on Wednesday. The other thing you're going to need to do for Thursday's class is you're going to need to find a current event article that you can read and understand on either nuclear fission or fusion, and it needs to be from within the last 6 months. Something in a newspaper is fine, but the biggest thing is make sure it's readable. Don't just search nuclear fission or fusion and come in with 10 pages of stuff you don't understand because it's above your head. All right, have a good day.